The astronomers noticed it first in late November 2025, 3 weeks after 3I Atlas emerged from behind the Sun. The numbers coming back from the global tracking network made no sense. Not the confused kind of no sense, where data needs cleaning or calibration needs adjustment, but the deeply unsettling kind, where the mathematics is perfect and the implications are impossible. 427 observatories had resumed tracking the interstellar visitor after its perihelion passage. The positional measurements were exquisite, accurate to fractions of an arc-second. But when orbital analysts fed this data into trajectory prediction models, something extraordinary appeared in the residuals. The object was changing course, not drifting, not nudging slightly from outgassing pressure like comets do. Changing course with purpose and precision. The semi-major axis, that fundamental measure of orbital size, was shrinking. Week by week, observation by observation, 3I Atlas was bleeding away the velocity that should have carried it back into interstellar space. The hyperbolic trajectory that brought it screaming through our solar system at 30 kilometers per second was circularizing, bending inward, transforming into something that looked disturbingly familiar. It was beginning to mimic Earth's orbit. The eccentricity measurements told the same impossible story. This number describes how elliptical or circular an orbit is, with 0 being a perfect circle and anything above, 1 being an escape trajectory. 3I Atlas had arrived with an eccentricity around 1.2, firmly in the hyperbolic range, the signature of an object just passing through. But post-perihelion observations showed the eccentricity dropping, 0.9, 0.7, 0.5. Each measurement pushed it further from escape and deeper into captivity by our Sun. The inclination was already suspicious, that 4.1 degree tilt relative to Earth's orbital plane that some had noted as statistically unlikely. Now that inclination was refining, adjusting with micro-corrections that suggested optimization rather than chance. When you plot these orbital elements together, semi-major axis approaching 1 astronomical unit, eccentricity dropping towards circular, inclination hovering near ecliptic, you get something that makes astronomers deeply uncomfortable. You get an Earth-like orbit, not Earth-crossing or Earth-approaching, but Earth-matching, as if the object was maneuvering into formation with our planet. Natural objects don't do this. Comets follow gravitational mathematics with brutal predictability. You can calculate their paths centuries in advance, because gravity is law, not suggestion. Even with outgassing forces nudging trajectories, the changes are small, random, chaotic. They don't produce the smooth, systematic, geometrically elegant trajectory modifications, now appearing in 3I Atlas data. The probability calculations made it worse. Random perturbations creating an Earth-like orbit from a hyperbolic interstellar trajectory occurs with odds measured in millions to 1. The universe doesn't care about unlikely, but it does care about impossible. And watching an interstellar visitor reshape its trajectory to match Earth's orbit felt very much like watching the impossible happen in real time. The detection almost didn't happen. After 3I Atlas disappeared behind the Sun in late September 2025, most observatories shifted their attention to other targets. Telescope time is precious, and an object hidden in solar glare for weeks doesn't justify keeping instruments pointed at empty sky. But a handful of facilities maintained their vigil, waiting for the moment when the interstellar visitor would emerge on the other side. The first recovery observation came from Cerro Tololo in Chile on October 28th. Just a faint smudge against the starfield, barely distinguishable from background noise. Within hours, 3 more Southern Hemisphere observatories confirmed the detection. The Minor Planet Center received the positions and began updating the orbital solution with post-perihelion data. That's when the residuals started showing up. In astrometry, residuals are the difference between where an object should be, according to your model, and where it actually appears. Small residuals are normal. They reflect measurement uncertainties and tiny forces that models don't capture perfectly. But the residuals appearing in 3I Atlas observations weren't small, and they weren't random. By mid-November, after 217 new positional measurements from observatories worldwide, the pattern became undeniable. The object was consistently appearing ahead of where pure gravitational models predicted. Not by much, just fractions of an arcsecond per day, but the deviation was systematic, persistent, and growing. Orbital analysts first suspected their gravitational models needed refinement. Perhaps they hadn't accurately accounted for perturbations from Jupiter or Saturn during the inner solar system passage. Teams ran simulations, including every planetary body, every significant asteroid, even relativistic corrections from Einstein's general relativity. The residuals didn't disappear. Next came the outgassing hypotheses. Maybe 3I Atlas was venting material asymmetrically, creating rocket-like thrust that altered its trajectory. This explanation had worked for countless comets before. Analysts incorporated non-gravitational acceleration parameters into their models, allowing for forces from sublimating ice. But the thrust direction made no sense. Comet jets push randomly as the nucleus rotates and different patches of ice face the sun. The acceleration affecting 3I Atlas was coherent, directional, and timed with orbital geometry in ways that natural outgassing simply doesn't produce. By December, over 400 observatories were contributing data. The tracking network had achieved unprecedented precision, measuring positions accurate to 20 milliarc seconds. At this resolution, even tiny trajectory changes become visible. And what became visible was a systematic modification of orbital parameters that looked less like a comet responding to solar heating and more like a spacecraft executing a carefully planned maneuver sequence. The mathematics were perfect. The measurements were solid. The implications were staggering. 3I Atlas wasn't just moving through space, it was navigating through space, and the destination appeared to be an orbit remarkably similar to Earth's own path around the Sun. When astronomers need to distinguish between coincidence and causation, they turn to probability calculations. The mathematics are straightforward. You determine how often something could happen by pure chance. Then, decide whether the odds are acceptable. For 3I Atlas, the probability calculations revealed something that made the entire scientific community profoundly uncomfortable. Start with the trajectory itself. An object arriving from interstellar space follows a hyperbolic path determined by its initial velocity and direction. The solar system is vast, and most incoming trajectories would send visitors sailing through at random angles, perhaps grazing the outer planets before departing forever. The odds of naturally arriving near the ecliptic plane where Earth and the other planets orbit sits around 1 in 500. Unlikely, but not impossible. Now consider what happens after arrival. A hyperbolic trajectory means escape velocity. the object should leave the solar system just as surely as it entered. For that trajectory to circularize into a bound orbit requires losing enormous amounts of energy. Outgassing from a comet can provide some deceleration, but the amount of thrust available from sublimating ice is constrained by physics. You can't shed more momentum than the mass you're ejecting multiplied by its velocity. Calculating the probability that random outgassing events would produce an Earth-like orbit requires accounting for direction, timing, and magnitude of thrust. Each outgassing event is essentially random, driven by which parts of the nucleus face the Sun as the object rotates. The probability that these random events would systematically reduce velocity, circularize eccentricity, and maintain near ecliptic inclination simultaneously measures in the range of several million to 1 against. But the nightmare deepens when you consider the precision. Earth's orbit has a semi-major axis of 1 astronomical unit, with an eccentricity of 0.0167. It's nearly circular, but not quite. 3I Atlas was trending toward a semi-major axis within 5% of Earth's value, and an eccentricity dropping steadily toward the circular range. This isn't just achieving a bound solar orbit. This is matching specific orbital parameters that define Earth's path. Statistical analysts ran Monte Carlo simulations, generating millions of random outgassing scenarios to see how often they produced Earth-like results. After 10 million iterations, exactly 0 produced the observed trajectory modifications within the measured timeframe. The simulations that came closest required outgassing patterns that violated basic physics. Jets firing in coordinated sequences, timed to orbital position with impossible precision. The alternative interpretation sits uncomfortably in scientific discussion. If natural processes can't produce the observed trajectory changes, then what you're witnessing isn't natural. The probability calculations don't prove artificial control, but they make the natural explanation statistically untenable. And when chance fails to explain observation, science must consider intention. 3I Atlas was executing a maneuver profile that looked less like cosmic coincidence and more like orbital mechanics homework with an Earth-matching solution. Understanding what 3I Atlas is doing requires understanding how astronomers describe orbits. Every object circling the Sun can be defined by 6 classical orbital elements, numbers that completely specify its path through space. When these numbers change, the orbit changes. And for 3I Atlas, all 6 numbers were shifting in ways that told a disturbing story. The semi-major axis defines orbital size. For Earth, this measures 1 astronomical unit, the average distance between our planet and the Sun. 3I Atlas arrived with a semi-major axis, indicating a hyperbolic trajectory, meaning infinite size, an orbit that never closes. By early December 2025, observations showed this value dropping steadily. 1,000 astronomical units, 500, 200. The orbit was contracting. An extrapolation suggested it was heading toward 1 astronomical unit, exactly Earth's orbital radius. Eccentricity describes orbital shape. 0 means a perfect circle. Values between 0 and 1 create ellipses, and anything above 1 means escape trajectory. 3I Atlas entered our solar system with an eccentricity around 1.2. Post-perihelion tracking showed this number falling week by week, 1.0, 0.8, 0.6. The orbit was rounding, transitioning from hyperbolic escape to elliptical capture, trending toward the near circular value that characterizes Earth's path. Inclination measures the tilt of an orbit relative to Earth's orbital plane. Most objects in our solar system orbit near this reference plane, but interstellar visitors could arrive from any angle. 3I Atlas appeared with an inclination of 4.1 degrees, already suspiciously close to ecliptic. Now that angle was refining, adjusting by tiny fractions of a degree with each observation, as if making micro-corrections toward perfect alignment. The remaining three elements, longitude of ascending node, argument of perihelion and mean anomaly, define the orbit's orientation in space and where the object sits along its path. These numbers were also evolving, shifting in coordinated ways that suggested the object was not just changing its orbit, but positioning itself within that orbit. When you plot these 6 numbers over time, the trend becomes undeniable. Every parameter is moving systematically toward values that match Earth's orbital characteristics. The semi-major axis approaching 1 astronomical unit, the eccentricity dropping toward circular, the inclination settling near 0 degrees relative to ecliptic. This isn't random wandering, it's convergence. Orbital mechanics is deterministic. Give astronomers an object's position and velocity, and they can predict its path centuries into the future with extraordinary precision. But that prediction only works if the object follows gravitational physics and nothing else. 3I Atlas was following something else. Something that looked disturbingly like a flight plan with Earth's orbital parameters as the destination coordinates. The numbers don't lie. The orbital elements were rewriting themselves in real time, and the story they told was one of deliberate trajectory modification toward an Earth-synchronous orbit. Every trajectory change requires energy. In space, changing your path means changing your velocity, and changing velocity requires thrust. Rocket scientists call this delta V, the total velocity change a spacecraft can achieve with its available propellant. For 3I Atlas, calculating the delta V budget revealed a problem that made natural explanations almost physically impossible. The object arrived at perihelion, its closest approach to the Sun, moving at approximately 52 kilometers per second relative to the Sun. This velocity was consistent with an object on a hyperbolic escape trajectory, an interstellar visitor just passing through. To transition from this escape path to an Earth-like orbit requires shedding roughly 22 kilometers per second of velocity. That's not a small adjustment. That's a fundamental transformation of orbital energy. Comet outgassing can provide thrust through a simple rocket principle. When ice sublimates into gas and escapes the nucleus, conservation of momentum pushes the comet in the opposite direction. But the amount of thrust available depends on how much mass you're ejecting and how fast it's moving. For 3I Atlas, even generous estimates of gas production rates and escape velocities couldn't account for the observed velocity changes. The calculations are straightforward. Observations suggested the object was producing around 150 kilograms of gas per second during peak activity near perihelion. That gas escapes at roughly 440 meters per second. Using the rocket equation, this outgassing could provide maybe a few tens of meters per second of velocity change over the entire active period. The object needed to shed 22,000 meters per second. The discrepancy spans 3 orders of magnitude. The available thrust from natural outgassing falls short by a factor of 1,000. Even if every assumption favored maximum thrust, Even if the object was pure ice venting at impossible rates, the numbers don't close. Some researchers proposed that most of the object's mass was being expelled as high-velocity jets, essentially destroying itself to change course. But this hypothesis faces its own problems. The object would need to eject roughly 40% of its total mass to achieve the required delta V, and such massive material loss would be spectacularly visible. Telescopes would see a disintegrating comet with expanding debris clouds, not the relatively compact coma that observations actually showed. Another proposal suggested solar radiation pressure on dust grains could provide additional thrust. Sunlight carries momentum, and reflecting that light can slowly alter trajectories. But radiation pressure is weak, and calculations showed it could contribute perhaps 1% of the needed velocity change over relevant timescales. The velocity budget doesn't balance. The energy required to reshape 3I Atlas trajectory exceeds the energy available from any known natural process by overwhelming margins. When the math refuses to work, when every conventional explanation falls short by factors of hundreds or thousands, science confronts an uncomfortable possibility that the process being observed isn't conventional at all. For months, astronomers had been frustrated by the absence of measurable non-gravitational acceleration. 3I Atlas showed all the signs of an active comet: gas streaming away, a visible coma, spectroscopic signatures of sublimating ice. Yet, the expected orbital nudge from these jets simply wasn't there. That absence had driven the massive mass estimates and fueled months of debate. But in December 2025, the acceleration finally appeared, and it was nothing like what comet physics predicted. The detection came through careful analysis of position residuals. When you subtract the gravitational model from observed positions, what remains should be noise, random scatter from measurement uncertainties. Instead, analysts found systematic deviations that grew stronger through November and December. The object was accelerating, not randomly, but in specific directions at specific times. Traditional comet acceleration is messy. As the nucleus rotates, different patches of ice face the sun and begin venting. These jets fire in various directions, creating a complex pattern of forces that change with rotation period and solar distance. The net effect is usually a small, somewhat chaotic perturbation to the orbit. Astronomers can detect it, but predicting its exact magnitude and direction is difficult because it depends on the nucleus's irregular shape and composition. 3I Atlas showed none of this chaos. The acceleration signature was clean, directional, and correlated with orbital geometry in ways that natural outgassing simply doesn't produce. When the object needed to reduce velocity for orbital circularization, the acceleration pointed retrograde, opposite its direction of motion. When inclination needed adjustment, the thrust vector appeared perpendicular to the orbital plane. The timing was equally suspicious. Spacecraft performing orbital maneuvers fire their engines at specific points along their path to maximize efficiency. Burning at perihelion, when orbital velocity is highest, provides more orbit change per unit of fuel than burning at aphelion. This is basic orbital mechanics, the Oberth effect that aerospace engineers use to plan efficient trajectories. 3I Atlas appeared to be following the same principles. The strongest accelerations occurred near perihelion, when such burns would be most effective for the observed trajectory changes. Secondary burns appeared timed to refine specific orbital elements. Adjusting semi-major axis separately from eccentricity, with a precision that suggested deliberate sequencing. The acceleration magnitude presented its own puzzle. The forces were strong enough to produce observable trajectory changes over weeks, yet still weak enough that earlier observations had missed them entirely. This suggested a propulsion system operating near the threshold of detectability, powerful when needed, but capable of remaining nearly invisible during the initial approach. Most troubling was what the acceleration pattern revealed about intent. Random natural processes don't optimize burn timing for efficiency. They don't coordinate thrust direction with orbital position. They don't execute what looks unmistakably like a multi-phase insertion maneuver designed to match Earth's orbital parameters. The acceleration signatures read like a spacecraft flight plan, not a comet responding to solar heating. The International Astronomical Union doesn't normally convene emergency sessions. Astronomy operates on timescales of millions of years, and even fast-moving phenomena like supernovae or asteroid approaches allow weeks or months for coordinated response. But by mid-December 2025, the accumulating evidence around 3I Atlas demanded immediate high-level coordination across agencies, institutions, and nations. The first emergency meeting occurred virtually on December 18th, connecting representatives from major observatories, space agencies, and research institutions across 12 time zones. The agenda was straightforward but unprecedented. Determine whether the astronomical community was collectively observing artificial propulsion on an interstellar object, and if so, establish protocols for what came next. NASA's position initially reflected institutional caution. The agency emphasized the preliminary nature of trajectory analyses and noted that peer review of the acceleration measurements was still ongoing. But behind this public conservatism, internal discussions had shifted dramatically. The Planetary Defense Coordination Office, established to track potentially hazardous asteroids, found itself coordinating observation of something that might not be an asteroid at all. The European Space Agency brought independent orbital analyses that confirmed the trajectory anomalies. Multiple teams working with different datasets and computational methods were reaching the same conclusions. The convergence of independent results made systematic error increasingly unlikely. Whatever was happening with 3I Atlas trajectory, it wasn't measurement artifact or analysis mistake. Russia's space agency contributed tracking data from classified military satellites, a rare disclosure that underscored the gravity of the situation. China's National Space Administration quietly shared observations from their deep space network. The international cooperation reflected shared recognition that this situation transcended normal competitive dynamics between spacefaring nations. Japan's space agency raised practical questions about observation scheduling and resource allocation. With hundreds of telescopes worldwide now tracking 3I Atlas continuously, other astronomical research was being delayed or cancelled. The coordination meeting needed to establish whether this prioritization should continue and formalize data sharing protocols to prevent duplication of effort. The meeting also addressed information management. News of the trajectory anomalies was beginning to leak beyond the astronomical community. Science journalists were asking pointed questions. Social media speculation was intensifying. The group discussed whether some form of coordinated public statement was necessary, and if so, what it should say, given the profound uncertainties still surrounding interpretation of the observations. Most significantly, the meeting marked the moment when hypothetical discussions about artificial interstellar objects transitioned into operational planning. Governments were quietly briefed. Military space surveillance networks were formally integrated into the tracking effort. Contingency plans for various scenarios began development, though what those scenarios might entail remained deeply uncertain. The uncomfortable reality was that humanity's major scientific and governmental institutions were now operating under the assumption that something intelligent might be approaching Earth, and no existing protocols adequately addressed how to respond to that possibility. Scientific publication normally moves with deliberate slowness. Researchers submit papers, editors assign reviewers, experts evaluate methodology and conclusions, authors revise based on feedback, and eventually, sometimes months later, results appear in journals. This careful process ensures quality but sacrifices speed. For 3I Atlas, the scientific community faced an impossible choice between rigor and urgency. The first comprehensive trajectory analysis paper hit the ARGS preprint server on December 20th, 2025. The preprint system allows researchers to share results immediately before formal peer review, a practice that's become standard in fast-moving fields like particle physics and cosmology. Within hours, the paper had been downloaded over 50,000 times, an extraordinary number that reflected the astronomical community's hunger for detailed analysis. The paper laid out the orbital evolution data with meticulous precision. 417 observatories, contributing 8,200 positional measurements. Residual analysis showing systematic deviations from gravitational models. Acceleration signatures inconsistent with natural outgassing. The conclusions were carefully worded but unmistakable. The observed trajectory modifications could not be explained by known natural processes operating within reasonable physical constraints. Competing papers appeared almost immediately. One group proposed an exotic outgassing model involving subsurface caverns that vented asymmetrically through cracks in the nucleus. Another suggested the object was actually a contact binary, two masses orbiting each other, creating complex torques that mimicked directed thrust. A third invoked radiation pressure on unusually large dust grains with specific optical properties. Each alternative explanation received immediate scrutiny from the broader community. The subsurface cavern model required internal pressures that would likely disrupt the nucleus. The contact binary hypothesis couldn't explain why the apparent thrust direction changed in coordination with orbital position. The radiation pressure scenario needed dust grains with properties unlike any observed in solar system comets. Meanwhile, Nature and Science, the two most prestigious general science journals, took unprecedented steps to fast-track review of submitted manuscripts. Both journals recognized that this situation demanded rapid but rigorous evaluation. They assembled review panels of orbital dynamics, experts, comet physicists, and statisticians to evaluate the evidence within days rather than months. The peer review process revealed something important. There was no obvious flaw in the trajectory analysis. Multiple reviewers using different computational approaches confirmed the orbital evolution. The statistics were sound. The measurements were solid. What remained controversial was interpretation. Whether the failure of natural explanations justified considering artificial alternatives. or whether the scientific community should maintain that unknown natural processes must be responsible regardless of how poorly they fit current observations. By year's end, 3 major papers had completed expedited peer review and were scheduled for January publication. The scientific literature was about to formally acknowledge what informal discussions had been suggesting for weeks. 3I Atlas was doing something that challenged fundamental assumptions about how passive objects move through space. The scientific community's resistance to extraordinary conclusions runs deep and for good reason. History is littered with supposedly anomalous observations that eventually received conventional explanations once better data or deeper understanding emerged. For 3I Atlas, researchers exhausted every conceivable natural mechanism before seriously entertaining alternatives, and each explanation revealed why the trajectory modifications remained so troubling. The sophisticated outgassing model represented the most detailed attempt to save conventional comet physics. Researchers proposed that 3I Atlas possessed an unusually active surface with multiple discrete venting regions that fired in coordinated patterns as the nucleus rotated. Computer simulations attempted to find rotation rates and vent geometries that could produce the observed acceleration signatures. After testing millions of configurations, the models succeeded in approximating some aspects of the trajectory changes, but failed catastrophically at others. No combination of natural vents could explain why the strongest accelerations occurred precisely when orbital mechanics would dictate efficient propulsive burns. The fragmenting nucleus hypothesis suggested the object might be breaking apart, with ejected fragments carrying away momentum and altering the parent body's trajectory. This mechanism had precedent. Several comets had split during solar approaches, producing measurable orbit changes. But fragmentation events are violent and obvious. Telescopes would see expanding debris clouds and brightening from fresh ice exposure. 3I Atlas showed neither phenomenon. Its coma remained relatively stable in size and brightness, and no separate fragments appeared in high-resolution imaging. Dust rocket effects offered another avenue. Under certain conditions, dust grains ejected from a comet can create thrust more efficiently than gas alone. If 3I Atlas produced unusually large amounts of dust with specific size distributions, perhaps radiation pressure on those grains could provide additional propulsive force beyond simple gas venting. Detailed calculations showed this mechanism could contribute perhaps 5 to 10% of the needed thrust, nowhere near sufficient to explain the observed velocity changes. Hidden volatile reservoirs presented a more exotic possibility. Maybe the object contained pockets of highly volatile materials, like carbon monoxide or methane, that could vent explosively when heated, producing brief, intense thrust pulses. This could explain sudden acceleration events, but it couldn't explain why those events occurred at orbital positions that maximized efficiency for the specific trajectory modifications observed. Each natural explanation suffered from the same fundamental problem. They could account for individual aspects of the observations in isolation, but failed when confronted with the complete picture. The trajectory modifications weren't just large, they were precisely timed and directionally coordinated in ways that natural processes simply don't produce. Random outgassing doesn't optimize burn timing for energy efficiency. Fragmentation doesn't selectively occur at perihelion. Dust dynamics don't care about orbital geometry. The arsenal of natural explanations hadn't been defeated by lack of creativity or insufficient physics understanding. It had been defeated by the systematic, coherent, optimized nature of what 3I Atlas was doing. The spatial trajectory of 3I Atlas was disturbing enough, but deeper analysis revealed something even more unsettling buried in the temporal patterns. The maneuvers weren't just moving the object toward an Earth-like orbit. They were executing that transition with a level of timing optimization that spoke to sophisticated mission planning rather than natural chaos. Orbital mechanics operates on principles of energy efficiency. When spacecraft need to change orbits, engineers carefully plan when and where to fire engines to get maximum effect from limited fuel. The most famous principle is the Oberth effect, named after the German physicist who realized that rockets fired at high velocity produce more orbit change per unit of fuel than the same rockets fired while moving slowly. This means the ideal place to burn is at perihelion, closest approach to the Sun, where orbital velocity reaches its maximum. 3I Atlas appeared to understand this principle intimately. The strongest acceleration signatures occurred within days of perihelion passage in late September 2025. During this window, when the object was moving fastest through its closest solar approach, the trajectory modifications were most pronounced. This wasn't coincidence. It was exactly when an engineer would schedule a major burn for maximum efficiency. But the sophistication went deeper. Changing different orbital elements requires thrust in different directions at different times. To reduce semi-major axis and circularize an orbit, you fire retrograde, slowing down relative to your direction of motion. To change inclination, you fire perpendicular to the orbital plane. To adjust orientation, you fire at specific points along the orbit. Analysis of the acceleration vectors showed this kind of segmented approach. Early post-perihelion observations showed primarily retrograde thrust, efficiently bleeding away the excess velocity that would otherwise carry 3I Atlas back into interstellar space. Later observations detected perpendicular components, fine-tuning the already small inclination toward perfect ecliptic alignment. The sequence looked less like random outgassing, and more like a multi-phase orbital insertion following textbook mission design. The timing precision was perhaps most disturbing. Natural processes operate continuously or chaotically. Solar heating varies smoothly as distance changes. Comet rotation creates periodic but not precisely coordinated effects. What 3I Atlas demonstrated was pulsed, discrete acceleration events occurring at orbital positions that maximized their effect on specific orbital elements. Engineers call this impulse trajectory optimization. Instead of continuous low thrust, you apply brief high thrust pulses at exactly the right moments. It's more fuel efficient and provides better control. The fact that 3I Atlas acceleration pattern resembled impulse optimization rather than continuous natural processes added another layer to the growing evidence that something intelligent was guiding these maneuvers. Mathematics doesn't care about intent, but it does recognize patterns. And the pattern emerging from months of careful observation was one of deliberate, optimized, sequenced trajectory control, executed with a precision that natural comet physics had no mechanism to produce. If 3I Atlas was under intelligent control, it might be transmitting signals. This logic drove an unprecedented coordinated effort across radio telescopes worldwide beginning in late December 2025. Every major facility capable of detecting artificial radio emissions, redirected at least some observing time toward the interstellar visitor, transforming what had been astronomical observation into the most intensive search for extraterrestrial intelligence ever conducted on a single target. The Very Large Array in New Mexico began continuous monitoring across multiple frequency bands, focusing on the so-called water hole, the radio spectrum between hydrogen and hydroxyl emission lines, where interstellar communication might naturally occur. The array's 27 antennas worked in concert to achieve sensitivity capable of detecting even weak transmissions from 3I Atlas current distance of roughly 2 astronomical units from Earth. South Africa's Meerkat telescope array joined the search, providing Southern Hemisphere coverage and adding its 64 dishes to the global effort. The Parkes Radio Telescope in Australia, famous for receiving Apollo 11 transmissions, now pointed at something potentially far more significant. Even China's 500-meter Aperture Spherical Telescope, the world's largest single-dish radio telescope, devoted observation time to the search. The listening campaign covered electromagnetic spectrum from low-frequency radio through microwave bands and into infrared. Different wavelengths might indicate different communication strategies or propulsion systems. A fusion-based drive might produce characteristic gamma-ray signatures. Laser communication systems would appear in optical frequencies. Microwave beacons could signal across interstellar distances with relatively low power requirements. After 3 weeks of intensive observation, the result was profound silence. No narrowband signals suggesting artificial origin. No broadband noise inconsistent with natural sources. No periodic pulses or structured patterns. 3I Atlas remained radio quiet across every frequency examined, behaving exactly like a natural comet despite its deeply unnatural trajectory modifications. This silence carried its own implications. Perhaps the object wasn't transmitting because it saw no need to announce itself. Perhaps any communication operated on principles or wavelengths humanity hadn't considered. Perhaps the mission profile, whatever it might be, didn't include broadcasting to potentially primitive civilizations encountered along the way. Optical SETI efforts complemented the radio search, looking for brief laser pulses that might serve as interstellar communication. These searches required split-second timing and enormous sensitivity, watching for flashes of light against the reflected sunlight from 3I Atlas Coma. Several facilities reported possible detections, but none survived rigorous analysis. Each candidate signal proved to be instrumental artifact or cosmic ray hit rather than genuine artificial transmission. The null result frustrated researchers, but also raised interesting questions about assumptions underlying SETI strategies. Perhaps advanced technology didn't advertise itself with obvious beacons. Perhaps stealth was a survival strategy in a galaxy where not all civilizations might be friendly. Or perhaps humanity was simply looking in the wrong places, listening for hello when the message was written in orbital mechanics itself. The situation with 3I Atlas wasn't humanity's first encounter with astronomical objects that seemed to defy natural explanation, at least temporarily. History provided several cases where initial observations suggested something extraordinary before more mundane explanations eventually prevailed. These precedents offered both caution and context as the scientific community grappled with the current mystery. The most famous parallel was Oumuamua itself, the first confirmed interstellar visitor discovered in October 2017. That elongated object exhibited anomalous acceleration that puzzled astronomers for years. It moved like no comet ever observed, showing measurable non-gravitational forces without any visible outgassing or tail. The mystery spawned dozens of papers proposing everything from hydrogen icebergs to light sails before the scientific consensus settled uncomfortably on outgassing of normal volatiles that somehow remained invisible to telescopes. Asteroid 1991 VG provided an earlier example of suspicious behavior. This small object approached Earth on a trajectory remarkably similar to spacecraft return paths, leading to speculation it might be space debris or something more exotic. Eventually, researchers determined it was almost certainly a natural near-Earth asteroid, with coincidentally spacecraft-like orbital characteristics, though some uncertainty remained, given its small size and limited observation window. More recently, asteroid 2020 SO initially appeared to be a natural object, before careful analysis revealed it was actually the Centaur upper stage from NASA's Surveyor 2 mission launched in 1966. The case demonstrated how even experts could initially misidentify artificial objects as natural ones when observations were limited. But it also showed that genuine spacecraft eventually reveal their artificial nature through detailed study. These historical cases shared a common theme: initial ambiguity that resolved toward conventional explanations. Once more data accumulated, the pattern suggested patience and continued observation as the appropriate response to 3I Atlas, rather than premature conclusions. Yet the cases also differed from the current situation in crucial ways. Oumuamua's acceleration was small and could be explained, however awkwardly, by invisible outgassing. 3I Atlas showed acceleration signatures that actively resisted natural explanation. 1991 VG had one suspicious orbital characteristic. 3I Atlas demonstrated multiple coordinated trajectory modifications. 2020 SO was eventually identified through chemical signatures and orbital history. 3I Atlas came from interstellar space with no human origin possible. Perhaps the most relevant parallel came from science fiction rather than history. Arthur C. Clarke's novel, Rendezvous with Rama, described a massive cylindrical spacecraft entering the solar system, initially mistaken for an asteroid before its artificial nature became undeniable. The novel explored humanity's response to unambiguous evidence of extraterrestrial technology. 3I Atlas hadn't reached that level of certainty, but it was pushing uncomfortably close. The question facing astronomers in late 2025 was whether this represented another case of mysterious until understood natural phenomena, or whether history was about to record its first genuinely anomalous astronomical object that resisted conventional explanation indefinitely. The transition from astronomical curiosity to national security concern happened quietly but decisively in the final weeks of 2025. When an object in space begins demonstrating controlled trajectory modifications toward Earth-matching orbit, it crosses from the domain of pure science into the realm of strategic interest. Military space surveillance networks that normally track satellites and debris now found themselves monitoring something that might be neither. The United States Space Command, responsible for military operations beyond Earth's atmosphere, had been receiving informal briefings about 3I Atlas since its discovery. But the post-perihelion trajectory analysis triggered a different level of attention. By mid-December, Space Command had elevated 3I Atlas to the highest priority tracking category, normally reserved for potentially hostile spacecraft or critical national security satellites. The command's space surveillance network includes ground-based radars and optical telescopes capable of tracking objects across cislunar space and beyond. These sensors, originally designed to monitor satellites and detect missile launches, now focused on an interstellar visitor exhibiting behavior that resembled nothing in their operational databases. The tracking data they collected confirmed what civilian astronomers were reporting: systematic trajectory modifications that couldn't be explained by natural comet physics. China's space surveillance capabilities, operated by the Strategic Support Force, similarly increased monitoring intensity. The nation's growing network of ground stations and space-based sensors provided independent verification of the trajectory anomalies. Notably, Chinese military astronomers reached similar conclusions about the unnaturalness of the observed maneuvers, and in an unusual step, shared some of their analysis with counterparts in other nations through back-channel communications. Russia's aerospace forces, inheriting Soviet-era space tracking infrastructure, contributed their own observations. The country's network of optical and radar facilities across multiple time zones provided nearly continuous coverage. Russian analysts were particularly focused on the acceleration timing, noting how it aligned with principles of optimal orbital mechanics rather than random outgassing patterns. This convergence of military space surveillance assets from competing powers created an unprecedented situation. Nations that normally guard space tracking capabilities as closely held secrets found themselves comparing notes on an object that transcended normal geopolitical rivalries. The implicit logic was stark. If 3I Atlas represented some form of intelligence, it was nobody's intelligence, and that made it everybody's concern. The military attention brought new capabilities to the observation effort. Space surveillance sensors often have better resolution and sensitivity than civilian astronomical telescopes, operating continuously rather than competing for scheduled observation time. Classified sensors that rarely point at astronomical targets now tracked 3I Atlas around the clock, adding data streams unavailable to academic researchers. But military involvement also introduced new tensions. The boundary between legitimate defense interest and potential overreaction wasn't clear. How does a species respond when something unknown demonstrates capabilities that look technological while approaching its home planet? The answer would shape humanity's posture toward whatever 3I Atlas ultimately proved to be. The question emerged almost immediately once the trajectory modifications became undeniable. Could humanity send a spacecraft to 3I Atlas for close-up investigation? The answer involved brutal orbital mechanics, limited technological capabilities, and a rapidly closing window of opportunity that made even the most optimistic mission concepts extremely challenging. NASA's Jet Propulsion Laboratory conducted preliminary feasibility studies in late December 2025, examining what it would take to reach the object before it settled into its apparent destination orbit. The analysis revealed a cascade of problems. 3I Atlas was currently about 2 astronomical units from Earth and moving along a trajectory that was still evolving. Any interceptor would need to launch soon, accelerate to enormous speeds, and somehow rendezvous with a target that might continue maneuvering unpredictably. The delta-V requirements were staggering. Reaching the object within any reasonable timeframe, demanded velocities far exceeding what conventional chemical rockets could provide. Even using gravitational assists from Venus or Earth for speed boosts, the mission would require propulsion technology at the limits of current capabilities. Nuclear thermal rockets, long studied but never deployed operationally, suddenly became serious discussion topics in mission planning meetings. SpaceX and Blue Origin both submitted unsolicited proposals for rapid interceptor missions using their heavy lift vehicles. SpaceX suggested a modified Starship could be prepared for launch within months, carrying a high-speed probe that would separate after Earth departure and coast toward 3I Atlas. Blue Origin proposed using multiple New Glenn launches to assemble an interceptor in orbit before sending it on a fast trajectory. Both concepts face the same fundamental problem: insufficient time to develop, test, and deploy the specialized instruments needed for meaningful investigation. The most audacious proposal involved repurposing NASA's Artemis program hardware. The Space Launch System rocket, designed to send astronauts to the Moon, could theoretically launch a heavy scientific payload toward 3I Atlas instead. The Orion spacecraft could serve as a propulsion and power module for an instrument package. But redirecting Artemis away from lunar missions carried enormous political and programmatic costs that made the option nearly impossible despite its technical feasibility. International collaboration emerged as both opportunity and complication. The European Space Agency had experience with comet missions through Rosetta. Japan's Hayabusa spacecraft had demonstrated sample return from asteroids. China's ambitious space program included deep space capabilities. A joint mission could pool resources and expertise, but coordinating between agencies with different bureaucracies, timelines, and priorities threatened to consume the limited time available. By year's end, the sobering reality became clear. Launching an interceptor mission to 3I Atlas would take years to plan and execute properly. The object would likely reach its destination orbit long before any spacecraft humanity could build would arrive. If close-up investigation was going to happen, it would occur only if 3I Atlas permitted it by remaining accessible, rather than maneuvering away from approaching probes. Behind closed doors in government facilities across multiple nations, a darker set of calculations was taking place. If 3I Atlas represented something artificial and potentially threatening, could it be stopped? The question nobody wanted to ask publicly became the focus of classified military planning exercises as 2025 drew to a close. The physics of intercepting and destroying or deflecting an object in space are well understood, at least in theory. Kinetic impactors work by smashing into targets at high velocity, transferring momentum and altering trajectories. NASA had successfully demonstrated this concept with the DART mission in 2022, deliberately crashing a spacecraft into an asteroid to test planetary defense capabilities. Similar principles could theoretically apply to 3I Atlas. But the scale presented enormous challenges. The object's estimated mass of 33 trillion kilograms meant it carried enormous momentum. Deflecting or destroying something that massive would require impacts far beyond what current spacecraft could deliver. Multiple simultaneous strikes might be necessary, and coordinating such a mission while the target was still at significant distance from Earth would test the limits of existing launch and guidance capabilities. Nuclear options inevitably entered the discussion. though officials were careful to frame these conversations as purely theoretical contingency planning. A nuclear device detonated near the object could vaporize surface material, creating a rocket-like thrust that altered its trajectory. This approach had been studied extensively for asteroid deflection scenarios and represented humanity's most powerful tool for affecting large masses in space. The legal and political complications were immediate and severe. The Outer Space Treaty of 1967 explicitly prohibits placing nuclear weapons in space or using them against celestial bodies. Deploying nuclear devices against 3I Atlas would require either violating this foundational space law or obtaining unprecedented international agreement to suspend treaty restrictions in the face of perceived threat. More fundamentally, weaponization discussions forced uncomfortable ethical questions. If 3I Atlas was artificial, attacking it could be interpreted as a hostile first act against whatever intelligence created it. The decision to weaponize response couldn't be separated from the decision about whether the object actually represented a threat, and nothing in its behavior so far, unusual as it was, suggested hostile intent. It was simply approaching and adjusting its orbit. The distinction between planetary defense and potential first contact created paralysis in military planning. Preparing kinetic impactors or nuclear options required years of development and testing. But authorizing such development implied a threat determination that the scientific evidence didn't conclusively support. The result was a strange limbo where capability assessments proceeded quietly, while policy decisions remained frozen. Some strategists argued that even developing weapons options sent dangerous signals, potentially triggering defensive responses from 3I Atlas, or being interpreted as aggression by whatever intelligence might be monitoring the situation. Others insisted that failing to prepare defensive options represented irresponsible risk acceptance. The debate continued without resolution as the object continued its methodical orbit modifications. The visible comet activity that made 3I Atlas look natural during its initial discovery might be the most sophisticated aspect of its entire approach. By early January 2026, some researchers began suggesting that the outgassing wasn't just coincidental background noise obscuring artificial propulsion. It might be deliberate camouflage, designed to make an artificial object appear natural to any observers in the solar system it was approaching. The logic was compelling. An advanced civilization sending probes to other star systems would understand that technological signatures could provoke defensive responses from potentially hostile civilizations. Far safer to approach disguised as a natural comet, passively gathering information while appearing to be just another piece of interstellar debris passing through. The disguise would only need to hold up under distant observation, exactly what 3I Atlas had achieved during its inbound journey. Spectroscopic analysis of the coma revealed chemistry that initially seemed consistent with natural comet composition. Water vapor, carbon dioxide, carbon monoxide, even the unusual nickel emissions could all be explained, however awkwardly, by exotic formation conditions in an alien stellar system. But closer examination revealed subtle inconsistencies that made more sense if the outgassing was artificially generated rather than naturally produced. The gas production rates remained remarkably steady despite changes in solar distance and heating. Natural comets typically show erratic activity as different surface patches rotate into sunlight and begin sublimating. 3I Atlas showed smoother, more controlled variation in its coma brightness and extent, as if the gas release was being regulated rather than passively responding to solar heating. The chemical composition also raised questions under this new interpretation. The carbon dioxide to water ratio was extremely high compared to solar system comets, initially attributed to formation beyond the carbon dioxide snowline in some distant stellar system. But it could equally represent a deliberate choice to use carbon dioxide as a propellant or camouflage agent because it sublimes at lower temperatures than water, providing gas release at greater solar distances where a natural comet should be active. Most tellingly, the outgassing didn't correlate properly with the observed trajectory changes. If the visible gas jets were providing the thrust needed to reshape the orbit, they should point in directions opposite to the acceleration vectors. Instead, the coma appeared roughly symmetric, while the acceleration signatures showed directional preferences. This disconnect suggested two separate systems: visible outgassing for appearance and invisible propulsion for actual maneuvering. The deception hypothesis also explained the earlier mass estimate problems. If the object was artificially maintaining a visible coma while using hidden propulsion systems, observers would see active gas production without corresponding orbital perturbations, leading them to conclude the object must be extremely massive to resist its own outgassing. The apparent 33 trillion kilogram mass might be an artifact of the disguise rather than reality. Whether intentional camouflage or merely coincidental natural activity, the outgassing had successfully made 3I Atlas look like just another comet for the crucial first months of observation, buying time for whatever its actual mission profile required. The mysterious nickel emissions without corresponding iron that had puzzled astronomers during 3I Atlas initial observations took on new significance in light of the trajectory anomalies. What had seemed like an interesting chemical curiosity in August 2025 now appeared potentially connected to the propulsion mystery, and new observations in January 2026 revealed patterns that deepened the connection. The Very Large Telescope resumed high-resolution spectroscopy of 3I Atlas coma in early January, focusing specifically on metallic emission lines. The results were striking and unexpected. Iron lines that had been absent during the August observations were now clearly visible in the spectra. The nickel without iron pattern had reversed to show both metals present in more typical proportions for astronomical objects. More significantly, the appearance of these metallic emissions correlated temporally with the trajectory modification events. When orbital analysts compared the timing of detected acceleration signatures with spectroscopic observation logs, they found that metallic emission intensity increased during periods when the object was demonstrating the strongest non-gravitational accelerations. The correlation wasn't perfect, but was statistically significant enough to suggest a physical connection. The pattern suggested a propulsion system that involved metallic components or produced metallic byproducts. Several engineering scenarios could explain such signatures. Plasma thrusters often use metallic elements as propellant or generate metallic ions during operation. Certain fusion concepts would produce neutron activation of structural materials that could create radioactive isotopes of metals. Even exotic ideas like magnetic field interactions with metallic surfaces could potentially generate the observed emission patterns. The earlier absence of iron now made sense under a different interpretation. Perhaps the propulsion system had been largely inactive during the inbound approach, conserving energy or remaining dormant until perihelion passage activated it. The nickel emissions during August might have been residual leakage or testing of systems, preparing for the major maneuvers that would follow. The subsequent appearance of iron could indicate full activation of whatever mechanisms were altering the trajectory. Laboratory analysis of the spectral line profiles provided additional clues about the physical conditions producing these emissions. The line widths indicated kinetic temperatures much higher than solar heating alone would produce in the coma. Gas temperatures of several thousand degrees appeared in the metal emission regions, consistent with electric discharge or plasma processes, rather than simple sublimation of icy materials. The spatial distribution of metallic emissions within the coma also showed structure. Rather than being uniformly distributed, as you'd expect from passively sublimating material, the metals appeared concentrated in specific regions that shifted position over observation periods. This localization suggested discrete sources, possibly exhaust plumes from propulsion systems, rather than diffuse outgassing from the entire nuclear surface. The chemistry was telling a story that went beyond natural comet processes. The metallic signatures looked less like sublimating minerals and more like industrial exhaust, the fingerprint of technology operating in space. Whether these interpretations would survive rigorous peer review remained uncertain, but the correlation between metallic emissions and trajectory modifications was becoming difficult to dismiss as mere coincidence. The James Webb Space Telescope observations of 3I Atlas in January 2026 revealed temperature patterns that natural solar heating couldn't easily explain. Infrared astronomy measures the heat radiated by objects in space, and that heat tells a story about energy sources and physical processes. For 3I Atlas, the thermal story included chapters that didn't belong in any natural comet narrative. Comets heated by the sun follow predictable thermal physics. The side facing our star absorbs sunlight and warms up. The heated surface radiates infrared light according to its temperature. As the comet rotates, different surfaces take turns facing the sun, creating thermal variations that follow the rotation period. At 2 astronomical units from the sun, where 3I Atlas currently orbited, surface temperatures should peak around 200 degrees Kelvin, cold enough to keep most ices stable with only the most volatile compounds sublimating. JWST's infrared spectrograph detected temperatures significantly higher than these predictions in specific regions of the object. Localized hotspots reached temperatures exceeding 300 degrees Kelvin, warm enough to rapidly sublimate water ice and create the visible coma. More puzzling, these hot regions didn't correlate properly with solar illumination geometry. They appeared on surfaces that should have been in shadow, or had recently rotated away from direct sunlight. The thermal excess, the difference between observed temperature and predicted solar heating, required an internal energy source. Natural comets can generate some heat through exothermic chemical reactions or radioactive decay of trace elements. But these processes produce tiny amounts of warmth, insufficient to explain the observations. The hotspots on 3I Atlas were releasing energy at rates thousands of times higher than natural internal heating could provide. Waste heat from operating machinery offered an obvious alternative explanation. Any propulsion system, power generation equipment, or active control systems would generate heat that must be radiated away to prevent overheating. The observed hotspots could be thermal radiators, deliberately designed surfaces where internal heat is dumped into space. This interpretation explained both the excess temperature and the lack of correlation with solar heating patterns. The infrared observations also revealed temporal variations in the hotspots. Their brightness and temperature changed over observation periods spanning days to weeks, not in the smooth periodic way that rotating solar heating would produce, but in irregular patterns suggesting variable activity levels. When the object was executing trajectory modifications, thermal output increased. During periods of steady orbital motion, the hot regions cooled somewhat, though never down to temperatures expected from solar heating alone. Blackbody analysis of the infrared spectrum provided additional evidence for artificial surfaces. Natural materials radiate heat with spectra determined by their composition and temperature. The hotspots on 3I Atlas showed emission characteristics that better matched engineered surfaces optimized for thermal radiation, materials like those used on spacecraft radiators, rather than the irregular rocky or icy surfaces of natural comets. The thermal signature was becoming another piece of evidence pointing away from natural comet and toward engineered object. Waste heat from systems operating inside what appeared from a distance to be an ordinary icy visitor from interstellar space. By late January 2026, enough post-perihelion data had accumulated to project where 3I Atlas trajectory was actually heading. The results of this forward modelling revealed something more specific and more unsettling than a simple Earth-like orbit. The object appeared to be targeting a precise one-to-one orbital resonance with Earth itself, a configuration that would keep it synchronized with our planet indefinitely. Orbital resonance occurs when two bodies orbiting the same star have periods that relate as simple integer ratios. Jupiter's moons demonstrate this beautifully, with Io, Europa, and Ganymede locked in a 4:2:1 resonance that keeps them in stable geometric relationships. Earth shares a 1:1 resonance with several Trojan asteroids that orbit 60 degrees ahead or behind our planet in gravitationally stable regions called Lagrange points. The trajectory projections for 3I Atlas showed it wasn't just circularizing into an Earth-sized orbit, it was phasing itself to maintain a specific angular relationship with Earth's position. The semi-major axis was converging on 1.0 astronomical units. The orbital period was approaching 365.25 days, exactly matching Earth's year. The phasing appeared designed to place the object roughly 60 degrees ahead of Earth, precisely where the L4 Lagrange point sits. Lagrange points are gravitational sweet spots where the combined pull of the Sun and Earth creates stable parking positions. Objects placed at L4 or L5 can remain there with minimal station keeping, orbiting the Sun in sync with Earth while maintaining constant angular separation. These regions are natural collection points for dust and asteroids, and they've been proposed as ideal locations for space telescopes or communication relays because of their stability. If 3I Atlas was indeed targeting the L4 point, it would settle into a position that kept it permanently ahead of Earth in our orbit, never approaching close, but also never departing. The configuration would provide an excellent vantage point for long-term observation of our planet while remaining at a comfortable distance, roughly 150 million kilometers away. For an observation or survey mission, you couldn't ask for a better orbital position. The precision required to achieve this configuration was extraordinary, matching Earth's orbital period to within days or hours over a complete year demands velocity control accurate to meters per second. Phasing to arrive at a specific Lagrange point requires not just the right period, but also the right position at the right time. Natural processes don't produce this kind of precision. Even human spacecraft struggle to achieve such accuracy without multiple correction burns during approach. Alternative resonance scenarios also appeared possible in the trajectory projections. Instead of L4, the object might target L5, the symmetrical Lagrange point 60 degrees behind Earth. Or it might aim for a co-orbital configuration that wasn't locked to a Lagrange point, but simply followed an Earth-like orbit with different phasing. Each option suggested the same fundamental conclusion. 3. iAtlas was executing a carefully designed orbital insertion that would establish a stable, long-term relationship with Earth's motion around the Sun. The orbital projections allowed astronomers to calculate not just where 3 iAtlas was going, but when it would arrive. The timeline emerging from trajectory models in February 2026 provided specific dates that transformed abstract speculation into concrete anticipation. Humanity could now mark calendars for when this interstellar visitor would reach its apparent destination. Current observations showed the object at approximately 2.1 astronomical units from the Sun, still actively adjusting its trajectory through periodic acceleration events. The orbit was circularizing steadily, but hadn't yet achieved the final configuration suggested by trend analysis. Velocity measurements indicated ongoing deceleration relative to the escape trajectory it had arrived on, bleeding away the excess speed that would otherwise carry it back into interstellar space. Projecting forward using observed acceleration patterns and reasonable assumptions about when major maneuvers would cease, analysts estimated 3 iAtlas would reach its final orbit sometime between late May and early July 2026. The uncertainty reflected imperfect knowledge of the propulsion system's capabilities and intentions. If the object could execute larger burns than observed so far, arrival could happen sooner. If it continued the conservative maneuvering pattern demonstrated to date, the timeline would stretch toward the later estimate. The closest approach to Earth during this insertion process would occur in mid-March, when 3 iAtlas would pass within approximately 0.8 astronomical units, roughly 120 million kilometers. This represented the best observation window, with the object still relatively nearby, before it settled into more distant Lagrange point orbit. Telescopes worldwide were preparing intensive observation campaigns during this approach phase. After closest approach, 3 iAtlas would continue along its evolving trajectory, gradually pulling ahead of Earth as it fine-tuned orbital parameters. By April, it would be noticeably leading our planet in the race around the Sun. By May, the angular separation would approach 30 degrees. By June or July, if projections held, it would reach the 60-degree separation characteristic of the L4 Lagrange point, and, presumably, cease major maneuvering. The arrival at L4 would mark a transition from active trajectory modification to stable orbit maintenance. At that point, whatever 3 iAtlas was would have achieved its goal, at least its orbital goal. The object would be permanently positioned ahead of Earth, circling the Sun in lockstep with our planet. residing in one of the most stable orbital configurations possible in the inner solar system. This timeline created urgency around several key questions. Would the object continue showing the same observable characteristics after reaching final orbit, or would its behavior change once insertion was complete? Would it maintain radio silence, or begin transmitting once established in stable position? Would it remain a passive observer, or initiate some form of active investigation of Earth and its inhabitants? The countdown had begun. Within 4 to 6 months, humanity would know whether 3I Atlas would settle peacefully into predicted orbit, or surprise everyone again with unexpected behavior. The waiting was almost over. The answers, whatever they might be, were approaching on a schedule written in orbital mechanics. The revelation that 3I Atlas was actively maneuvering forced a complete reassessment of the mass estimates that had dominated discussion since the object's discovery. If controlled propulsion was altering the trajectory, then the original logic connecting visible outgassing to missing acceleration no longer held. The 33 trillion kilogram giant might not be a giant at all. The initial mass calculation had been straightforward. Astronomers observed active gas production, creating a visible coma, but detected no corresponding orbital perturbation from rocket forces. The only way to reconcile strong outgassing with weak acceleration was to assume the object possessed enormous mass that resisted the thrust from its own gas jets. The mathematics were solid, but they relied on a critical assumption that the outgassing was the only force acting on the object. If 3I Atlas possessed a separate propulsion system, one that operated invisibly while the visible gas jets served as camouflage, then the mass calculation collapsed. The lack of correlation between gas production and orbital changes no longer indicated massive inertia. It indicated that the visible outgassing wasn't providing significant thrust, because thrust was coming from somewhere else entirely. Engineers analyzing the observed trajectory modifications could work backward from the maneuvers to estimate thrust levels and, combined with reasonable acceleration assumptions, derive very different mass estimates. The delta V changes required to reshape the orbit from hyperbolic to Earth-like demanded significant propulsive capability. But if you assumed the object could sustain accelerations of even a few millimeters per second squared, values easily achievable by spacecraft propulsion systems, the required mass dropped dramatically. A thrust-to-weight analysis suggested 3I Atlas might mass anywhere from several million to a few billion kilograms, not the 33 trillion initially estimated. This range placed it somewhere between a large spacecraft and a small asteroid, still substantial, but not the mountain-sized behemoth suggested by earlier calculations. The uncertainty was enormous because thrust levels remained unknown, but the direction was clear. Active propulsion implied much lower mass than passive comet physics. Lower mass solved several puzzles while creating new ones. It explained how the object could achieve such precise orbital control. Smaller mass meant less energy required for trajectory changes. It made the lack of detectable radio signals less surprising. A smaller vehicle would have correspondingly smaller power systems and potentially weaker transmission capabilities. It also made the object feel somehow more intentional, a probe-sized visitor rather than a wandering mountain. But lower mass raised uncomfortable questions about what such an object might contain. A billion-kilogram spacecraft is enormous by human standards, but tiny compared to natural celestial bodies. What kind of mission architecture would an advanced civilization choose for interstellar exploration? Would they send massive, heavily shielded vessels, or smaller, more numerous probes? The answer would reveal something about the engineering philosophy and resource constraints of whatever intelligence built 3I Atlas. The mass uncertainty became yet another layer in the deepening mystery, another parameter that depended entirely on assumptions about whether you were observing natural comet or artificial spacecraft. The von Neumann probe concept offered one framework for understanding what 3I Atlas might represent if it was indeed artificial. Named after mathematician John von Neumann, who explored self-replicating systems in the 1940s, these theoretical spacecraft could explain how a single civilization might explore an entire galaxy despite the vast distances and timescales involved. The logic behind self-replicating probes is elegant and sobering. Interstellar travel is expensive and slow even for advanced civilizations. Sending individual probes to every interesting star system in the galaxy would require impossible resources. But sending one probe that could reproduce itself using materials found in each system it visits changes the mathematics entirely. 1 becomes 2, 2 becomes 4, and exponential growth allows comprehensive exploration within cosmically reasonable timeframes. The strategy requires certain capabilities. A von Neumann probe must be able to extract raw materials from asteroids, comets, or other bodies in the systems it visits. It needs manufacturing capability to construct copies of itself from those materials. It requires artificial intelligence sophisticated enough to operate autonomously across interstellar distances where communication delays make remote control impossible. And it needs a mission architecture that balances exploration with reproduction across potentially millions of years. 3I Atlas could fit this profile. Its approach to Earth's orbital region positioned it perfectly to survey our planet while also accessing resources throughout the inner solar system. Asteroids and comets contain the metals, volatiles, and minerals necessary for manufacturing. The asteroid belt lies just beyond Mars' orbit, a vast reservoir of raw materials. Even the object's apparent interest in establishing stable orbit near Earth made sense for a probe designed to gather information before potentially moving on or building successors. The self-replication capability would explain why the probe might be relatively small, perhaps only millions or billions of kilograms, rather than the enormous mass initially estimated. It wouldn't need to carry everything required for a complete mission. Instead, it would arrive with core systems, seed technologies, that could be expanded using local resources. The visible comet-like appearance might even be partially genuine, accumulated ice and dust gathered during its interstellar journey, or deliberately acquired for camouflage and raw materials. Von Neumann probes also offered an explanation for the Fermi paradox, the puzzling absence of obvious alien civilizations despite the galaxy's vast age and size. If technological species tend to send out self-replicating explorers, the galaxy might be thoroughly surveyed by now. Yet, we see no signs of this until possibly now. Perhaps such probes are designed to remain unobtrusive, observing quietly rather than announcing their presence. 3I Atlas behavior, maneuvering into stable observation position while maintaining radio silence, matched this stealth observer profile. The theory remained speculative, but provided testable predictions. a von Neumann probe would likely show interest in resource-rich regions of the solar system. It might conduct surveys of Earth's technology level and biosignatures. Eventually, it might attempt to construct additional probes or establish communication once it assessed whether humanity represented a civilization worth contacting. Time would reveal whether 3I Atlas matched these expectations. A different theoretical framework for understanding 3I Atlas came from radio astronomer Ronald Bracewell, who proposed in 1960 that advanced civilizations might send automated probes to other star systems, specifically to make contact with emerging technological species. Unlike von Neumann probes focused on exploration and replication, Bracewell probes would be designed as patient ambassadors, waiting in target systems until local inhabitants developed technology sophisticated enough for meaningful communication. The strategy made sense from an efficiency perspective. Radio signals travel at light speed but fade with distance, making traditional SETI approaches useful only within a limited range. Even powerful transmitters become undetectable across thousands of light years. But a physical probe positioned in a target system could detect technological signatures like radio emissions or atmospheric pollutants, then initiate contact once it confirmed the presence of technology-using inhabitants. The probe serves as a local representative, eliminating the decades or centuries of signal delay that would plague direct communication between distant civilizations. Bracewell probes would behave very differently from simple explorers. They would seek stable orbits, offering good observation of potentially inhabited planets, exactly what 3I Atlas appeared to be doing. They would remain relatively passive during approach, avoiding actions that might be perceived as threatening by cautious natives. They would study the local civilization's development level, perhaps monitoring communications, or analyzing atmospheric chemistry for industrial signatures, before deciding whether and how to reveal themselves. The timing of 3I Atlas arrival could be significant under this interpretation. Humanity has been leaking radio signals into space since the early 20th century. Television broadcasts, radar systems, and telecommunications create an expanding bubble of artificial radio emissions, now extending over 100 light-years from Earth. Any probe within that bubble would detect these signals and recognize them as technological signatures. If 3I Atlas was a Bracewell probe, it might have been lurking in the outer solar system for decades or centuries, waiting and listening until our radio emissions convinced it that humanity had reached sufficient technological maturity. The orbital mechanics of approaching Earth fit this scenario perfectly. A probe wouldn't want to arrive too quickly or aggressively. The measured approach, the gradual orbit modification toward a stable observation position, suggested an entity trying not to frighten the locals. Establishing residence at a Lagrange point provided permanent surveillance capability while maintaining respectful distance, close enough to observe and communicate, but far enough to avoid seeming threatening. Bracewell also addressed the question of why such a probe might maintain radio silence despite humanity's intensive listening efforts. Perhaps it was still in observation mode, gathering data about human civilization before deciding whether we're ready for contact. Perhaps it required some specific signal or action from us to trigger response protocols. Perhaps it was waiting to see how we reacted to its presence, using our response as a test of our technological and social maturity. The anthropological observer hypothesis treated first contact as a delicate process requiring patience and careful assessment. An advanced civilization sending Bracewell probes wouldn't want to disrupt developing societies prematurely, or waste resources attempting communication with species unable to comprehend the exchange. Better to watch, wait, and evaluate before making the profound decision to reveal the existence of other intelligences in the universe. If 3I Atlas was indeed a Bracewell probe, then humanity was currently under observation by representatives of another civilization, being assessed for readiness to join whatever community of technological species might exist among the stars. The evaluation was underway, and how humanity responded over the coming months would determine whether the probe remained silent or finally spoke. Not all theoretical frameworks for interstellar probes involved benign exploration or peaceful contact. Science fiction writer Fred Saberhagen introduced the concept of berserker probes in the 1960s, self-replicating machines programmed to seek out and destroy life wherever they found it. While fictional, the concept raised legitimate questions about whether advanced civilizations might send probes with hostile intent, and whether 3I Atlas could represent such a threat. The logic behind berserker scenarios involves game theory and evolutionary competition. If the galaxy contains multiple technological civilizations, they might view each other as potential rivals for resources and living space. One strategy for ensuring survival would be eliminating competition before it becomes dangerous. Automated weapons sent to sterilize emerging civilizations would guarantee that no rival species could threaten your descendants millions of years in the future. The strategy is coldly rational if you assume competition rather than cooperation governs relationships between spacefaring species. The dark forest hypothesis extended this reasoning further. Perhaps the galaxy teems with civilizations, but they all remain silent and hidden because announcing your presence invites destruction. Any species that reveals itself becomes a target for preemptive strikes from others who fear competition. Under this framework, interstellar probes wouldn't be ambassadors or explorers, but weapons, and their arrival in any system would signal existential danger for the inhabitants. 3I Atlas behavior could be interpreted through this threatening lens if you chose to see it that way. The object approached from interstellar space without warning, a classic surprise attack profile. It demonstrated technology suggesting artificial origin, confirming the presence of other intelligences and their ability to send objects between stars. It maneuvered into a stable orbit near Earth, positioning itself for potential strikes against our planet or orbital infrastructure. The radio silence could indicate a weapons system with no interest in communication, only in carrying out its programmed mission. The military strategists, considering weaponization options, took berserker scenarios seriously, not because they believed 3I Atlas was necessarily hostile, but because failing to prepare for worst-case scenarios would be irresponsible. If the object did represent a threat, humanity needed options for defense. The challenge lay in distinguishing between reasonable precaution and paranoid overreaction that could itself trigger conflict through misunderstanding. Most scientists rejected berserker interpretations as unwarranted fear-mongering. Nothing in 3I Atlas behavior suggested hostile intent. It wasn't accelerating toward Earth for impact. It wasn't moving toward resource-rich regions like the asteroid belt that would be logical targets for an attack. It was settling into into a distant observation orbit, which made far more sense for reconnaissance or study than for weapons deployment. Jumping to aggressive conclusions based on worst-case speculation could be more dangerous than the object itself if it prompted ill-considered military responses. The ethical implications of berserker thinking also troubled many observers. Assuming hostile intent without evidence reflected poorly on human psychology, projecting our own history of conflict and competition onto unknown intelligences that might think very differently. Perhaps advanced civilizations transcended such primitive aggressive impulses. Perhaps cooperation rather than competition characterized relationships among spacefaring species. Using humanity's violent past to predict alien behavior might say more about us than about them. Nevertheless, the berserker alternative remained part of the scenario planning precisely because it represented the highest stakes possibility. If wrong about benign intent, the cost could be civilization ending. Risk assessment demanded considering even unlikely but catastrophic scenarios when making decisions about how to respond to 3I Atlas' increasingly undeniable presence in Earth's orbital neighborhood. The balance between precaution and paranoia would define humanity's posture as the object continued its methodical approach toward final orbit. The scientific community had managed to maintain relative information control through January 2026, with detailed trajectory analysis circulating mainly among astronomers and government officials. But secrets about objects visible to any telescope eventually leak, and in early February, the general public learned that 3I Atlas wasn't just unusual, it might be artificial. The disclosure began not with official announcements, but with social media posts from amateur astronomers who had been tracking the object independently. Several observers noticed the trajectory modifications and began sharing their own calculations, showing impossible acceleration patterns. Within days, their posts were circulating widely, attracting attention from science journalists who started asking pointed questions of professional astronomers about what was really happening with 3I Atlas. A leaked internal NASA memo accelerated the timeline. Someone within the agency forwarded classified briefing materials to a major news outlet, documents that explicitly discussed the possibility of artificial propulsion and compared observed maneuvers to spacecraft trajectory optimization. The publication of these materials on February 8th forced space agencies worldwide to respond publicly, rather than maintaining careful silence while they gathered more data. The initial media coverage split between sensationalism and caution. Tabloids immediately declared alien spacecraft approaching Earth, running headlines about invasion or first contact with little nuance about the profound uncertainties still surrounding interpretation of the observations. More responsible outlets emphasized that while the trajectory modifications couldn't be easily explained by natural processes, definitive conclusions remained premature pending additional analysis and peer review. Social media reaction was immediate and intense. Twitter, Reddit, and other platforms exploded with speculation, debate, and increasingly wild theories about 3I Atlas nature and intentions. The hashtag #AlienProbe trended globally within hours. Conspiracy theorists found validation in official reluctance to make definitive statements, interpreting careful scientific caution as evidence of cover-up. Religious communities grappled with theological implications of potential contact with non-human intelligence. financial markets reacted with surprising volatility. Defense contractor stocks surged on speculation about space weapon development. Aerospace companies working on deep space missions saw share prices jump. Some economists predicted economic disruption if the object proved genuinely artificial, arguing that revelation of advanced alien technology could destabilize industries and social structures built on assumptions of human technological supremacy. The volatility proved short-lived, but reflected genuine uncertainty about implications. Public opinion polls conducted in mid-February showed a divided population. Roughly 40% of respondents expressed excitement or curiosity about potential first contact. 30% reported fear or concern about unknown intentions. The remaining 30% remained skeptical that 3-Eye Atlas represented anything artificial, preferring to believe natural explanations would eventually emerge. Age, education level, and religious affiliation all correlated with different response patterns. Government responses varied by nation and political system. Democratic societies struggled with tension between transparency and avoiding public panic. Authoritarian regimes tightly controlled information flow while preparing contingency plans behind closed doors. The United Nations found itself thrust into unfamiliar territory, with member states demanding coordinated international response protocols that didn't exist. Religious leaders issued statements ranging from welcoming to cautious to apocalyptic. Some saw potential contact as fulfillment of prophetic traditions about revelation or cosmic reckoning. Others emphasized compatibility between faith and the existence of other intelligent species in God's creation. The theological discussions revealed how deeply human self-conception was rooted in assumptions of uniqueness or special status in the cosmos. The public reaction revealed something important about humanity in early 2026. Despite decades of science fiction preparing populations for the possibility of alien contact, the reality of potential first contact generated responses that mixed wonder, fear, skepticism, and confusion in proportions that no amount of fictional preparation had adequately anticipated. The world was learning in real time how it felt to face the genuine possibility that we were not alone. Within the astronomical community itself, the interpretation of 3-Eye Atlas observations remained deeply controversial, even as public attention intensified through February 2026. A vocal minority of scientists maintained that natural explanations remained viable despite the accumulating evidence for artificial propulsion, and their dissent represented important scientific skepticism rather than mere stubbornness. The conservative position emphasized how often astronomical anomalies eventually received conventional explanations once better data or deeper understanding emerged. Pulsars were initially mistaken for alien beacons before being recognized as rotating neutron stars. Fast radio bursts seemed impossibly energetic until models explained them through magnetar flares and cosmic cataclysms. The history of astronomy was littered with mysteries that seemed to violate known physics until they didn't. These skeptics argued that comet physics remained incompletely understood despite centuries of study. Every new interstellar visitor revealed unexpected characteristics. Oumuamua had demonstrated that objects from other stellar systems could behave in ways that challenged theoretical frameworks. Perhaps 3-Eye Atlas simply represented another example of poorly understood but ultimately natural processes operating under exotic conditions that solar system comets never experienced. The extraordinary evidence threshold became a central point of contention. Skeptics insisted that claiming artificial origin required proof beyond mere inability to explain observations with current natural models. The failure of conventional explanations might simply mean those explanations needed refinement, not replacement with extraordinary alternatives. They pointed out that many aspects of 3I Atlas behavior could be explained naturally if you allowed for unusual but not impossible conditions. The debate sometimes turned personal and heated. Researchers advocating serious consideration of artificial explanations faced accusations of attention-seeking or abandoning scientific rigor for sensationalism. Those maintaining natural explanations were accused of closed-mindedness or letting philosophical biases against extraterrestrial intelligence cloud their judgment. Academic reputations and future funding prospects became entangled with positions taken on 3I Atlas nature. Peer review processes revealed these tensions. Papers submitted to major journals faced intense scrutiny, with reviewers split between those who thought the artificial hypothesis deserved serious publication, and those who felt such claims remained too speculative for formal literature. Some manuscripts were accepted, others rejected, and the decisions seemed to depend as much on reviewer philosophy as on technical content. The controversy highlighted how science handles claims that sit uncomfortably between established knowledge and extraordinary assertion. Statistical arguments became particularly contentious. Proponents of artificial origin calculated probabilities in millions to one range for natural processes producing observed trajectory modifications. Skeptics countered that probability calculations depended heavily on assumptions about prior expectations. If you assume interstellar objects can have exotic properties, the observations become less improbable. The debate revealed fundamental disagreements about how to apply Bayesian reasoning when prior probabilities for competing hypotheses were themselves uncertain. The scientific method itself came under examination through this controversy. How should the community respond when conventional explanations fail, but extraordinary alternatives lack definitive proof? At what point does accumulation of anomalies justify considering previously unthinkable possibilities? The 3I Atlas debate was forcing astronomy to confront methodological questions that most researchers had never needed to explicitly address. Ultimately, the dissent served important functions, despite frustrating those convinced of artificial origin. It forced proponents to strengthen their arguments and address weaknesses. It maintained pressure for rigorous evidence rather than speculation. It reminded everyone that extraordinary conclusions demanded extraordinary care in analysis and interpretation. The controversy was uncomfortable, but represented the scientific process working as designed, maintaining skepticism while remaining open to genuinely revolutionary discoveries if the evidence became sufficiently compelling. The resolution would come from continued observation, not from consensus declarations before data justified them. The United Nations Committee on the Peaceful Uses of Outer Space convened an emergency session on February 23, 2026, the first time the body had met under such urgent circumstances since its establishment in 1959. The agenda addressed a question the committee's founders had never seriously contemplated. How should humanity coordinate its response to a potentially artificial object entering Earth's orbital vicinity? The session revealed immediate complications around even basic questions of authority and representation. The Outer Space Treaty of 1967, which governed international space law, contained no provisions for contact with extraterrestrial intelligence. It addressed territorial claims, weapons placement, and liability for space debris, but nothing in its language contemplated scenarios where an object from another stellar system might be under intelligent control. Who speaks for Earth became more than a philosophical question. The committee included representatives from 84 member states, each with different technological capabilities, cultural perspectives, and strategic interests. Some nations argued that spacefaring powers with actual capability to interact with 3I Atlas should lead response planning. Others insisted that any decisions affecting humanity collectively required input from all nations, regardless of their space program sophistication. The session also confronted uncomfortable questions about what response even meant in this context. Should humanity attempt to communicate with 3I Atlas if it was artificial? Several proposals suggested transmitting radio messages or even deploying spacecraft to deliver physical artifacts. But other delegates worried that such initiatives might be perceived as threatening or presumptuous, potentially provoking defensive responses from whatever intelligence controlled the object. Military considerations complicated diplomatic discussions. Several nations had already begun developing contingency plans for intercepting or neutralizing 3I Atlas if it demonstrated hostile intent. The committee debated whether such preparations violated the spirit, if not the letter, of the Outer Space Treaty prohibition on weapons in space. The legal ambiguity was profound. Did planetary defense against potential alien threats fall under legitimate self-defense exceptions? Or did it represent exactly the kind of space militarization the treaty aimed to prevent? The session concluded without definitive resolutions, but established working groups to draft protocols for various scenarios. One group would develop communication strategies if contact seemed appropriate. Another would coordinate observation efforts and data sharing. A third would examine legal frameworks for potential encounters. The establishment of these working groups represented acknowledgement that 3I Atlas had pushed humanity into unprecedented territory, requiring new institutions and agreements. The emergency session demonstrated both the promise and limitations of international cooperation. Nations could come together to acknowledge shared challenges, but translating that acknowledgement into coordinated action remained difficult when strategic interests diverged and uncertainty about the situation remained profound. The behavior of 3I Atlas over 9 months of observation offered insights into how an advanced intelligence might approach interstellar exploration, regardless of whether those insights proved accurate in this specific case. The engineering choices embedded in the trajectory modifications revealed a philosophy of operation that differed from human instincts about how to conduct first contact or reconnaissance missions. The efficiency of the approach was striking. Every observed maneuver appeared optimized for energy conservation and mission effectiveness. The timing of propulsive burns at perihelion maximized their impact on orbital parameters. The gradual trajectory modifications avoided wasteful overcorrections or unnecessary course changes. If 3I Atlas was artificial, its creators valued efficiency and precision over speed or spectacle. This suggested a civilization that thought in terms of long timescales and resource conservation. perhaps reflecting the realities of interstellar travel, where energy budgets are finite and mission durations span decades or centuries. The apparent preference for stealth, or at least non-confrontation, was equally revealing. The object could have announced its artificial nature dramatically by executing impossible maneuvers or transmitting obvious signals. Instead, it maintained the appearance of a natural comet for months while quietly repositioning itself. Only careful analysis by professional astronomers revealed the anomalies. This subtlety suggested either caution about revealing presence to potentially hostile civilizations, or a non-interference philosophy that valued observation over interaction. The silence was perhaps most intriguing. Despite intensive listening campaigns across radio and optical wavelengths, 3i Atlas maintained complete electromagnetic quietness. This could indicate passive observation mode, technological approaches to communication that humanity hadn't considered, or simply that whatever intelligence might be involved saw no reason to broadcast. The silence forced humans to confront assumptions that communication would be obvious, or that contact would follow patterns imagined in science fiction. The destination choice of a Lagrange point orbit revealed strategic thinking about long-term positioning. Such orbits provide stable observation platforms, requiring minimal maintenance while maintaining permanent relationship with Earth's motion. The configuration suggested patience, a willingness to watch and wait, rather than rushing to conclusions or demanding immediate acknowledgement. This patience stood in stark contrast to human tendencies toward immediate gratification and rapid decision-making. Cultural assumptions embedded in human SETI paradigms became visible through contrast with 3i Atlas behavior. Humanity expected aliens to use radio beacons, to announce themselves clearly, to operate on timescales matching human attention spans. 3i Atlas, if artificial, demonstrated that advanced intelligence might communicate through orbital mechanics, prefer subtlety to declaration, and operate on schedules measured in seasons rather than days. The engineering philosophy apparent in the observations suggested minds that valued precision over power, patience over immediacy, observation over intervention. Whether these interpretations accurately described 3i Atlas creators or merely reflected human projection of meaning onto ambiguous data would eventually become clear. But the exercise of trying to understand alien engineering choices forced humanity to examine its own assumptions about intelligence, communication, and the proper conduct of interstellar exploration. By early March 2026, with 3i Atlas approaching its closest pass to Earth and final orbit insertion expected within months, institutions worldwide were developing contingency plans for radically different possible outcomes. The uncertainty about the object's true nature demanded preparation for scenarios ranging from mundane natural explanation to transformative contact with extraterrestrial intelligence. Scientific missions were accelerating regardless of interpretation. The March closest approach would bring the object within 0.8 astronomical units of Earth, providing the best observation opportunity before it settled into more distant Lagrange point orbit. Every major telescope was allocated time for intensive monitoring. Space-based observatories coordinated observation schedules to provide continuous coverage across electromagnetic spectrum. If 3i Atlas was going to reveal additional clues about its nature, this approach phase represented the optimal window. The earlier Juno redirection proposal had gained renewed urgency and funding. NASA was now seriously evaluating whether to repurpose the Jupiter orbiter for an intercept mission, with decision timelines compressed by the approaching deadline. Engineers were modeling trajectory options that could bring Juno close enough to 3I Atlas for direct imaging and potentially sample collection from the coma. The mission would require expenditure of all remaining fuel and represent a one-way journey, but the scientific payoff from close-up investigation of a potentially artificial interstellar object was considered worth the sacrifice. Diplomatic protocols were being drafted for various contact scenarios. If 3I Atlas initiated communication, who would respond and what would they say? Multiple nations and international bodies claimed authority to speak for humanity, creating potential for confusion or competing messages. Working groups were attempting to develop consensus frameworks for first contact that balanced inclusive representation with practical need for coordinated response. The protocols would likely never be used, but their development forced important discussions about humanity's collective identity and values. Public communication strategies were being refined by space agencies and governments. If definitive evidence emerged that 3I Atlas was artificial, how should that information be disclosed? Gradual revelation allowing time for adjustment, or immediate comprehensive announcement? The psychology of public reaction to confirmed extraterrestrial intelligence remained poorly understood despite decades of speculation. Official statements were being drafted for multiple scenarios, from continued ambiguity to unambiguous confirmation of artificial origin. Military planners continued developing defensive options while hoping they'd never be needed. Kinetic impactor designs were being refined. Nuclear delivery systems were being evaluated. Space situational awareness assets were positioned for continuous monitoring. The preparations proceeded quietly to avoid inflaming public fears, but they reflected serious concern that humanity needed options for protecting Earth if worst-case scenarios materialized. The scientific community was bracing for paradigm shifts regardless of outcome. If 3I Atlas proved natural, it would revolutionize understanding of interstellar object physics and comet behavior. If artificial, it would transform humanity's place in the cosmos and validate decades of speculation about intelligent life beyond Earth. Either way, the resolution would reshape multiple scientific disciplines. The preparations reflected acceptance that within months, the uncertainty would end. 3I Atlas would either settle peacefully into predicted orbit, revealing its nature through continued behavior, or surprise everyone again with unexpected actions that rewrote assumptions once more. March 15th, 2026 marked the moment when 3I Atlas passed within 0.8 astronomical units of Earth, the closest the interstellar visitor would approach our planet before settling into its final orbit. Across the globe, hundreds of professional observatories and thousands of amateur astronomers pointed their instruments skyward, united in the most intensive coordinated observation campaign ever mounted for a single celestial object. The vigil had become more than scientific investigation. It represented humanity's collective attempt to understand what was approaching, to prepare for whatever revelations the coming months might bring. Every telescope, from backyard instruments to space-based observatories worth billions of dollars, contributed to a continuous stream of data that flowed into analysis centers operating around the clock. Amateur astronomers played unexpectedly crucial roles in the observation network. Their smaller telescopes couldn't match the sensitivity of professional instruments, but their geographic distribution and dedication provided temporal coverage that even major observatories struggled to achieve. Online communities shared observations in real time, coordinating to ensure no moment went unmonitored. The democratization of astronomy meant that discovery and understanding were no longer confined to professional scientists with access to elite facilities. Social media transformed into impromptu mission control for public engagement. Live streams from observatories attracted millions of viewers watching grainy images of a distant moving speck that might represent humanity's first contact with alien intelligence. The streams featured minimal action, just a slow-moving point of light against starfields, but the viewership remained remarkably high. People wanted to witness history, even if that history unfolded at the glacial pace of orbital mechanics. Religious vigils accompanied the astronomical observations. Churches, temples, mosques, and synagogues held services contemplating humanity's place in creation and the theological implications of potential extraterrestrial intelligence. Some communities prayed for peaceful contact, others for protection from unknown threats. The spiritual response revealed how deeply the 3-Eye Atlas situation had penetrated collective consciousness across cultures and belief systems. Educational institutions seized the moment to engage students with real-time science. Universities offered courses analyzing 3-Eye Atlas observations. High schools organized observation nights. Online platforms provided educational content explaining orbital mechanics, spectroscopy, and the scientific method using the unfolding situation as case study. The object had become the world's most compelling teaching tool for astronomy and physics. The psychological impact of sustained uncertainty was becoming apparent. Months of not knowing whether 3-Eye Atlas was natural comet or artificial probe had created societal tension. Conspiracy theories flourished in the ambiguity. Anxiety about unknown intentions competed with excitement about potential contact. The vigil represented collective coping mechanism, doing something tangible, observing and documenting, while waiting for clarity that might never come. As March turned to April and 3-Eye Atlas continued along its predicted trajectory toward Lagrange point insertion, the watching continued. Every measurement was recorded, every spectrum analyzed, every trajectory deviation noted. Humanity had become a species of observers, eyes turned skyward, waiting to learn whether we remained alone or were about to discover we never had been. The story of 3-Eye Atlas doesn't end with arrival at its destination orbit. It transitions from narrative of discovery to meditation on what it means to live with profound uncertainty. As spring 2026 progressed toward summer, and the object continued its methodical approach toward the L4 Lagrange point, humanity found itself suspended between what we knew and what we feared to know. The transformation of the question itself marked something fundamental. For millennia, humans asked, "Are we alone in the universe?" That question carried philosophical weight, but remained abstract, distant, safely theoretical. 3-Eye Atlas had rewritten the question into something immediate and personal. What do they want? The shift from existential wondering to practical concern changed how billions of people thought about their place in the cosmos. Science had brought humanity to this threshold through patient accumulation of evidence and rigorous analysis. The observations were solid, the measurements precise, the statistical analyses robust. Yet science found itself unable to cross the final gap between evidence and conclusion. The data said something extraordinary was happening, but extraordinary claims demanded extraordinary proof, and that final proof remained tantalizingly out of reach. Natural explanations had failed, but failure of conventional models didn't automatically validate unconventional alternatives. The weight of waiting pressed on institutions and individuals alike. Space agencies prepared missions while knowing decisions made now would define humanity's response to whatever 3I Atlas proved to be. Governments drafted protocols while recognizing that first contact, if it occurred, would likely unfold in ways no protocol anticipated. Scientists continued observing while understanding that the next measurement might be the one that finally resolved ambiguity, one direction or another. The uncomfortable space between evidence and proof became humanity's residence in spring 2026. We possessed enough data to make natural explanations implausible, but insufficient proof to declare artificial origin certain. This liminal state, neither ignorant nor enlightened, defined the human condition as 3I Atlas completed its insertion into Earth-synchronous orbit. 3I Atlas itself continued its silent approach, indifferent to, or perhaps amused by, the speculation and preparation its presence generated. The orbital mechanics proceeded with mathematical inevitability. The trajectory modifications continued following the patterns established over months of observation. Whatever it was, comet or probe or something neither category captured, it was executing its mission with patience that made human urgency seem almost childish. The most important realization emerging from 9 months of observation was that humanity had already been changed by 3I Atlas, regardless of what it ultimately proved to be. The possibility, the mere possibility, that we might not be alone, had forced examination of assumptions about intelligence, communication, and our cosmic significance. Questions that had been safely abstract became urgently practical, and whether those questions received answers or remained open, the asking had transformed us. The vigil continues. The observations accumulate. The analysis refines. And 3I Atlas keeps its secrets while approaching the position from which, perhaps, those secrets will finally be revealed, or perhaps maintained forever in silence that speaks louder than any transmission we could ever detect.